very first speaker of the conference this year, apart from James, is Marton Soskuthy, like if the vowel harmony right? And we'll be talking about the role of phonetic biases in the emergence of allophonic splits. Thank you.
Thank you. Okay, so the topic for today's talk, as you can see, will be the role and the interaction of phonetic biases and the emergence of allophonic splits. And a little bit more specifically, what I'm going to show first is that you can use a usage-based model of production and perception to simulate allophonic splits and perhaps to help us understand allophonic splits. And then you can also see that actually some of the predictions of these models are borne out by the data as well. More particularly, what you can see is that frequency distributions within categories influence the likelihood of allophonic splits. And that's actually a very important result because that suggests that it is possible to predict sound change, at least to some extent, based on the structure of the lexicon. And I think that's a very interesting finding. Okay, so the structure of the talk is very simple. I'm going to first talk a little bit about phonetic biases and introduce the topic briefly. Then I'm going to present an example of an allophonic split, vowel lengthening before voiced obstruents. Then I'm going to present the simulation results, and finally I will talk about an empirical study. Okay, so in order to understand what I mean by phonetic biases and allophonic splits, it's very useful to distinguish between two types of contextual variation. And one of these is what I will call a phonetic bias. And what is quite crucial in this account is that I conceive of phonetic biases as completely universal and automatic. So this is just something that results from the way the human articulatory and perceptual system is set up. And there's another type of contextual variation which I will call allophonic variation. And the difference here is that this is not universal or automatic. This is something that language specific and learned. In some sense, it's controlled by the speaker. Okay. And what's really interesting is that if you look at these two different types of contextual variation, there's actually a very interesting correlation between the two, namely that phonetic biases are often paralleled by patterns of allophonic variation. And here's just one example. For instance, in probably every language, what you see is that vowels standing next to each other or in neighboring syllables influence each other, right? So the quality of the vowels can change slightly as a function of other neighboring vowels. But actually some languages show a much more robust version of this phenomenon, which is called vowel harmony. So for instance, in Hungarian or Finnish, you would see something like this. Okay. And one explanation for this type of parallelism has been that allophonic variation in fact results from the phonologization of phonetic biases. And this is in fact what I'm going to refer to as an allophonic split, sort of the passage of this automatic variation to a learned pattern of variation. Okay. And there are several questions that arise in connection with allophonic splits. One of them is, well, what's the mechanism behind them? And what I'm going to propose here is that a probabilistic category representation paired with a feedback loop could account for this, and you will see what I mean by that. Also, another question is whether there are any linguistic factors that can affect allophonic splits, and the answer will be, well, yes, the size of allophonic splits can actually be predicted to some extent from frequency distributions from within categories, as I've already noted. Okay. So let's talk a little bit about an example of allophonic splits then, which is vowel lengthening before voiced obstruents. It has been observed by many, many people that vowels are often longer before voiced obstruents than they are before voiceless ones. Here's an example from a very exotic language, English.
Bag.
This is bag.
Pack.
If you listen to the
bag. Pack.
The vowel is, you could say, sort of underlyingly the same, but in fact what you can see is that in bag it's significantly longer than in pack. And obviously this is a cherry-picked example. It shows it really nicely, and it's not always quite this clear, but in fact this effect holds quite robustly in a wide range of languages. So English, French, Lithuanian, Korean, Bengali, and many other languages in fact. Okay. What we also see is that this phenomenon is subject to cross-linguistic variation. So even though we find it in many, many languages, it's not necessarily present to the same extent. So what you can see is that, for instance, in English you have a really sizable, large effect, so they are really quite a bit longer before voiced obstruents. Whereas if you look at a language like French or Hungarian, you can see a much smaller effect there. Okay, it's still there, but it's not quite as robust. And people have suggested that this might actually be a reflection of the distinction between phonetic biases and allophonic variation. Also, if you look at one language, the size of this effect can vary across different vowels and different environments, which is actually something that I'm going to exploit in the empirical study. Okay. So let's move on to the simulation bit. What I'm going to try to do is to use a usage-based account of phonology, and here's a few examples of people who have used this type of model before, to try to see how allophonic splits could emerge. And I'm just going to very briefly lay out the steps in this particular simulation. I'm not going to talk about the underlying motivation for it, because people have talked about that elsewhere and I don't have the time, but I'm going to try to explain how it works. So the first step in this simulation is production. And production is imagined really simply here. You just sample a probability distribution. So here's an example. You have the goat vowel. This would be the distribution of tokens of the goat vowel along the dimension of length for, say, speakers Southern Standard British English. And what you can see here, this is the overall distribution, the black line and the grey shaded area. The blue line represents voiceless examples, so words like goat, and the red line represents voiced examples, so words like toad. Okay. And if I want to produce something, basically what I do is that I sample this distribution. But the way I sample it is that, in fact, because I know that, say, I want to produce the word toad, and it's in a voiced environment, the red distribution is going to have a greater influence. Okay, so it's slightly modified towards this sub-distribution within it. Okay, and this is production. Right, so once I have my production target, which in this case is this red line, phonetic biases have a chance to apply. And phonetic biases are really simple here. The target that comes out of the sampling is displaced slightly towards the bias attractor. Right? So this is all that happens. And in the simulations that I present, there are actually two biases. One of them is vowel lengthening in plus voiced environments, and the other one is actually a sort of a general vowel shortening bias. It's sort of a minimal effort principle. The idea is that you don't want to have vowels like ah, you have to shorten them at some point. Okay. And the third step in the simulation is feedback. So the new production, after you've applied the bias to it, is actually fed back into the category representation and modifies the category representation slightly. Okay. So this is actually the production target after it's been modified by the bias. If we add this to the distribution, then we see a slight shift. Okay. The overall distribution shifts, and what you can see even more is that the specific sub-distribution shifts as well. Okay. And these things are all connected through a process of iterated learning, which means that I just iterate these steps over and over. And this is actually a really nice illustration of the principle behind iterated learning. So this is a work of art by an artist called Daniel Bejar, and what he did is that he took his key, just flat I think, and he made a copy of it. And then he made a copy of that copy, and then he made a copy of the copy of the copy, and then he put all of these next to each other, and this is what he got. Right? And what's really interesting is that actually the steps of this process mirror the steps of the process that I've just described to you very closely. So what happens is that, well, production, sort of sampling the distribution is just copying the key itself, right? That's, you just want to get some sort of good representation. The bias is something in the machine that does the copying, which actually, as you can see in this case, sort of shifts everything a little bit towards the left. Which is quite interesting. We don't know why it's there, but obviously, so it's a very weak bias, but it seems to apply fairly consistently. And of course, feedback consists in the fact that at every case, the input to the copying is not the original key, but the last step in the copying. Okay? And if you do this, then you get this really nice, robust change through these very small steps. And this is, in fact, what happens in the simulation as well. Okay. So let me show you what the simulation looks like if I run it. So here what you have are basically exactly the same things as what I've talked about. So you have the overall distribution, you have the sub-distributions, you have the two biases, and let's just run the simulation. Okay, so what you can see is that the whole category moves a little bit towards this bias, but in fact the red sub-distribution is much further displaced towards the bias than the blue sub-distribution. Okay? And that's, of course, because voice tokens are affected by this bias, but not voiceless tokens. Right, so this is quite interesting on its own because it shows that it's possible to model allophonic splits in this framework. However, there's actually something much more important about this, and that's that, in fact, if we take this model, we can also infer some predictions from it. We can try to see whether it predicts any particular properties of these types of sound changes. And in fact, we can see that it does make a very interesting prediction. And we can see this prediction nicely if we look at frequency distributions of different environments within a given category. So let me explain what I mean by that. I think there's two kinds of frequency distributions that you could talk about here. One of them is quite simple. Bias proportion is the relative frequency of biasing environments in a category. Okay. So that means that, say, you have a category, say O, and O occurs a given number of times in a voiced environment and a given number of times in a voiceless environment. And bias proportion is just the proportion of the voiced environment to the voiceless one. There's actually 10 vowels from English. I took these frequency counts from selects, and I just looked at what the frequency distributions are. So for instance, if you look at the cut vowel, you can see that the proportion of voiced environments is very low compared to voiceless ones. So if you look at oo, what you can see there is that the voiced environment is actually quite numerous compared to the voiceless one. Probably in this case, this would be due to words like would, should, and could. In the case of up, the frequency of the voiceless one could probably be because of the word but, which would be fairly frequent. So this is bias proportion. The bias balance sort of derives from bias proportion. This just means, well, now I'm not concerned about which category is more frequent. I'm just concerned, or which environment is more frequent. I'm just concerned about how balanced the two distributions are. So as you go up here, the balance is obviously just the same as the proportion. But if you look here, where the voiced environment is more frequent, the proportion, the bias balance starts to go down again, right? Because it's at this point that the two environments are equal in frequency. And after that, there's a sort of imbalance. Okay, so how do these parameters affect the emergence of phonological splits? Intuitively, we could assume if there's an unbalanced frequency ratio, if one of the environments is very frequent compared to the other one, then there's going to be less independence between the two sub-distributions. They're sort of going to be joined together more closely, and the less frequent sub-distribution is just going to follow the more frequent one. Okay. In fact, what I've done is that I just took this simulation that I've just shown you and kept all the parameters constant and just varied bias proportion continuously. Okay, just try to see what happens if you change this parameter. And I ran 50 simulations, and here are the results, which you can see. The y-axis here is the difference between the voiced and the voiceless subdistributions. Okay, and the x-axis is the proportion of bias tokens. So that's sort of like, you know, how many voice tokens you have compared to voiceless ones. And what you can see really nicely is that, in fact, this distribution goes up, right up to the middle here, and then it starts going down again. Okay, so the difference grows first as the proportion grows, but then it goes down again. And what this means is that actually the degree of splitting is correlated with bias balance, but not with bias proportion, or at least not linearly. So that's actually quite interesting, right? You sort of predict if there's a big, if the distributions are quite balanced, then what you're going to see is quite a wide difference between the two subdistributions, but if it's not balanced, then you're going to see a smaller difference. So then the question is, well, can we test this prediction somehow? And we can, and this is what I'm going to do. I'm just going to show you a smaller empirical study that I conducted focusing specifically on this effect. So this was a cross-linguistic production study. As I said, I focused on cross-category differences in the size of the voicing effect. I had 3 languages, each of them with 2 subjects, English, French, and Hungarian. The stimuli were really simple. These were just monosyllabic CVC items, so things like bag, for instance, with voiced and voiceless final stops. I took 10 vowels from English, 6 vowels from French, and 7 vowels from Hungarian. The procedure was really simple. It was just a simple production experiment with a carrier sentence. Not necessarily the most natural situation, but very controlled, which I think in this case is good. Overall, I had 23 different categories. Just sum these up, that's what you get. And 922 tokens from the subjects, which is not the largest sample size, but I think it's something that we can work with. So what I did is that I took duration measurements for the vowels in each of the tokens. Then I converted these measurements to Z-scores for each subject, just to control for interspeaker variation. This is a sort of a normalization procedure. And this is a sort of a sneak peek into the results. This is actually, the different colors here are different languages. The different cells are different speakers. On the left, you can see the Z-score of the voiceless distribution, and on the right you can see the Z-score of the voice distribution. And this is just the length. And what you see is that in English we have a really big effect. In Hungarian, which is the green one, we have a slightly smaller effect, and in French we have an even smaller effect. But in all of these languages we do see a voicing effect, which is really good. So then what I did is that I looked at each of the categories from each of the languages, and I took these voiced-voiceless proportions, the bias balance, from 3 phonemically annotated corpora, from the Select corpus for English, from the Lexique corpus for French, and an annotated frequency list compiled by Stephen Grimes from the Hungarian National Corpus for Hungarian. Okay. And this is sort of the result itself, which is we have balance plotted here along the x-axis, right? So that's how balanced voiced and voiceless categories are within a given vowel category in a given language. And what you can see here is the length difference between the voiced and the voiceless subdistributions. And you can see that there is actually very significant correlation here if you just look at the categories independently. And even if you look at the languages separately, in each of these languages you find the same correlation, right? And that's the exact same thing as what came out of the simulations, which is really cool, because then we can see that in fact it seems like the simulation makes the correct predictions. Okay, so there was a very clear correlation between bias balance and the degree of splitting. I wanted to put a significance value to this as well. So what I did is that instead of just looking at the categories and thereby sort of reducing all the data set to 23 measurements, I actually plotted all the things, right? All the 922 tokens from the experiment, and I plotted them against bias balance, but in a way that the blue circles here represent voiceless tokens, so like goat, and the red ones voiced ones, like toad. And what you can see is that as you get away from the sort of zero, very imbalanced situation, the difference between the two grows. And sort of in statistical terms, this could be interpreted as an interaction between voicing and balance. So then what I did is that actually I put this into a very simple linear regression model, where I modeled duration as a function of a few different parameters: voicing cross the balance, vowel height, and the place of articulation of the second consonant. And I put these two things in because they have been shown to correlate with vowel length in a variety of languages. Okay. So these are the results from the multiple regression, and what you can see is in fact there were two significant predictors. One of them was vowel height, which actually came out very significant, and the other one was the interaction between voicing and balance, the effect that we've just seen. Okay. And actually the R-squared value, sort of the coverage of the model is really good for this type of data, and the model itself is very significant. So that's great, because it seems like, you know, no matter how I look at this effect, I got a very robust and very significant result. Okay, so let me just briefly summarize this. What we saw is that if we use a usage-based model to simulate allophonic splits, then these splits just emerge naturally. The degree of splitting was predicted to be correlated with the amount of balance among the frequencies of different environments within a category. And this came out of the simulation, and also we saw the same thing in the results of the empirical study. And I think the most important message is that it seems to be the case that it's possible to make predictions with respect to the likelihood and the size of splitting in a given category based on lexical frequencies, which I think is something quite interesting. Thank you.
Time for questions? Yeah, I'll let you.
Yeah.
Do you have an explanation for the very different pattern of vowel length before obstruents in Scottish English, which would presumably have a similar balance profile?
Right. So. I mean, I don't know if anybody's looked at this, at the size of the voicing effect in different categories in Scottish English. I don't know if there's any data relating to that. I saw some.
Data. I mean, so before, the pattern is that vowels before voiceless stops compared to vowels before voice stops within a single morpheme are very similar. There's a tiny difference in the way that you would expect,
right,
but very small, so 10% or less. And then the salient differences happen before morpheme boundaries, so the classical
right, yes.
Past tense morpheme introduces a longer vowel, but
right, but so that's the Scottish vowel lengthening.
That's right.
Yeah.
But before, I mean, just within morphemes, vowels before voice consonants are very similar to vowels before
right.
voiceless consonants.
Well, I mean, I guess one explanation, and this is certainly not something that emerges from a simple model like this, could be that there is already, in fact, a sort of a very strongly phonologized and very robust effect, the Scottish vowel lengthening rule, and that might, in fact, affect these sort of smaller tendencies in a way that they are going to be realized more categorically. I mean, this is, in fact, what we see in some languages where there's a vowel length contrast. So say, I think this is found for Lithuanian, that in fact in that language what you could see is that most vowels had short and long versions, and that this was a phonemic distinction. But in fact there was one particular vowel which didn't have a long pair. And in that one vowel there was actually a very robust difference, and in the other vowels there was a smaller difference. So it seems like perhaps this more phonologized length distinction might interact in a way with this process that you get a smaller effect. I don't know if that answers your question.
So,
yes.
I mean, would you want to say, because you're talking about the emergence of an allophonic split, that has emerged in English and in non-Scottish English, and it hasn't emerged in French and Hungarian, which are very similar? You're just seeing there the universal bias, and then what's happened in Scottish English is something beyond the simple allophonic split.
I mean, yeah. So that's a difficult question, and I think it this sort of relates to what James was talking about as well with tones, whether you can call something tone or not. I mean, the way I see it is more of a gradient distinction. So I'm not really sure I can say that English has this thing and the other languages don't have this thing. I think you know, you can sort of arrange them on a scale, which is not to say that you couldn't get something more categorical. And I think perhaps Scottish English would be a good example of that with the vowel lengthening rule, which is, you know, sort of beyond the things that we see in standard British English or Southern British English, and the things that we see in Hungarian and French, which seem to be sort of there's more overlap between the two sub-distributions. It's intuitively it seems less categorical, whereas the Scottish vowel lengthening rule seems much more like that. I don't know if that's.
I have one quick one. Are there any common patterns in the way different vowels get are balanced or imbalanced across? So like some types of certain vowels with certain phonetic features tend to be more balanced or imbalanced or that sort of thing.
In terms of frequency?
Yeah.
Well, I mean that's a good question. Whether there are some factors that would in fact predict the frequency differences as well.
Mm-hmm.
I'm not really sure, to be honest. I mean, in English actually it was quite interesting because what was pretty clear is that there was a greater balance in the long vowels. This was a sort of a strange correlation between these two variables. But in fact, that's not entirely true, because in English what you see is that there's another vowel which is sort of long, but it's not really long, or it depends on how you look at it, which is a. And in the case of a, you could also see this big imbalance in the frequency. So that might actually have to do with the fact that a behaves in that particular way. I think I'm not really sure if it's possible to predict this, because it's always going to depend on very, you know, sort of random factors within the lexicon. The proportion is determined by them, so I'm not really sure if you could make any.
Just one.
Yeah.
Thanks very much.